Let's begin by talking about neurons. In a neural network, a neuron is the basic building block, much like the neurons in our brains. It's responsible for taking in information, processing it, and then passing it along to the rest of the network. You can think of it as a decision maker. It receives inputs, applies some processing based on parameters it has learned, and then produces an output. Now, if we look at this diagram, we can see a simplified version of a neural network. It's made up of three layers: the input layer, the hidden layer, and the output layer. Each of these layers plays a specific role in processing data and creating an output. Let's break them down one by one. Input layer. First, we have the input layer, which is the starting point of the neural network. This is where the raw data is fed into the system. In the diagram, we see three inputs: input 1, input 2, and input 3. These could represent any data points you want to analyze, numbers or features about the data you're working with. Each input represents a specific characteristic or feature of the data. Hidden layer. Next, these inputs are sent to the hidden layer, where the actual processing happens. This is where the network learns patterns and relationships in the data. In the diagram, we see that the hidden layer contains neurons called process 1 and process 2. These neurons perform calculations based on the inputs. We call it the hidden layer because the calculations happening here are not directly visible, they are part of the network's internal learning process. Output layer. Finally, once the hidden layer has processed the data, it passes the results on to the output layer. The output layer generates the final prediction or result. Depending on the task, this result could be a number, a category, or some other type of information. Now that we understand the layers, let's talk about two key components that make neural networks work: weights and biases. Weights. In the diagram, you'll notice that each connection between layers has a weight. These weights determine how important each input is to the next layer. For example, input 1 is connected to process 1 with a weight called weight 1. Similarly, input 2 has a weight called weight 2. Weights adjust the influence of each input on the network's final output. A higher weight means that input has a stronger impact on the result. Biases. In addition to weights, each neuron in the hidden and output layers has a bias. In the diagram, you'll see bias 01, bias 02, and bias 03. Biases are additional values that are added to the weighted sum of the inputs before producing the output. You can think of them as small adjustments that fine-tune the final result. Even if all the inputs are 0, the bias ensures that the neuron can still produce an output. Let's now walk through an example to see how the network calculates the final output step by step. Step 1. Calculating the hidden layer outputs. We'll start by calculating the outputs of the neurons in the hidden layer process 1 and process 2 using simple numbers. Let's assume input 1 is equal to 4. Input 2 is equal to 6. Input 3 is equal to 8. Also, the weights and biases are as follows. Weight 1 is equal to 0.5, weight 2 is equal to 0.3, and weight 3 is equal to 0.7. Bias 01 equals 1 and bias 02 equals 2. Now, we'll calculate the outputs of process 1 and process 2. For process 1, hidden neuron 1. Input 1 4 is multiplied by weight 1 0.5. For times 0.5 is equal to 2. Input 2 6 is multiplied by weight 2 0.3. 6 times 0.3 is equal to 1.8. Now, we add bias 011 to the sum of these two values. 2 plus 1.8 plus 1 is equal to 4.8. So, the output of process 1 is 4.8. For process 2, hidden neuron 2. Input 3 8 is multiplied by weight 3 0.7. 8 times 0.7 is equal to 5.6. We then add bias 022. 5.6 plus 2 is equal to 7.6. So, the output of process 2 is 7.6. Step 2. Calculating the final output. Now, we'll use the outputs from the hidden layer to calculate the final result in the output layer. We have weight 4 is equal to 0.6. Weight 5 is equal to 0.4. Bias 0.3 equals 0.5. For the final output, process 1 output for 0.8 is multiplied by weight for 0.6. For 0.8 times 0.6 is equal to 2.88. Process 2 output 7.6 is multiplied by weight 5 0.4. 7.6 times 0.4 is equal to 3.04. Add these two results and include bias 0.30.5. 2.88 plus 3.04 plus 0.5 is equal to 6.42. So, the final output of the network is 6.42. By following these steps, you can see how inputs are processed through the network, how weights and biases affect the final result, and how the output is calculated. This basic example shows the core principles behind how neural networks operate.